Now we've covered special functions called inverse trigonometric functions, and we've looked at calculating the derivative of these. What we have to be able to do is relate these to integrals as well, so the reverse process of differentiation. Now when it came to differentiating these, we had a standard format that we used. Integrating the functions goes along a similar path. We just have to work back the way from the standard derivatives that we had before. Now from the previous chapter, what we know is that d by dx, the derivative of sine minus 1x, is equal to 1 over the square root of 1 minus x squared dx. Now what we can do is reverse this. So if we take the integral of 1 over square root of 1 minus x squared dx, we're able to say that that's equal to sine minus 1 of x plus c. What we're able to do is take this and generalise it. And what we're able to say is the integral of 1 over a squared minus x squared is equal to sine minus 1 of x over a plus c. So we're able to generalise it in that manner there. Now we're able to use a fairly straightforward technique in order to be able to prove that this is the case. Let's imagine that we want to calculate the integral of 1 over the square root of a squared minus x squared dx. Now if I take the square root on the bottom, let's focus on that to begin with, and I factorise a squared out from both terms, I get the square root of a squared bracket 1 minus x over a all squared. What I can then do is separate this, and I know that that's then the square root of a squared times the square root of 1 minus x over a squared. Now remember, I've not put a squared with a 1 because 1 squared is 1, but technically it's written there as a power. So I can then write this part here as a. So I'm able to rewrite the bottom of this integral and make it the integral of 1 over a times the square root of 1 minus x over a squared dx. Now the 1 over a I can take out as it's just a constant, so I end up getting 1 over a times the integral of 1 over square root of 1 minus the x over a squared dx. What I'm then able to do is integrate that function, and I'll have 1 over a times sine minus 1 of x over a plus c. Now remember, the reason I've got the a here is if I take the derivative of this here, I've got to use the chain rule and multiply by the derivative of x over a. So having this here cancels that out, as I'm not going to have that a in the integral here. So that's why we've got the a outside. I can then cancel those out, and I get sine minus 1 of x over a plus c. So exactly what we were after when we wrote it down. Let's look at an example of that. So if I want to find the integral of dx over the square root of 5 minus x squared. So it takes the format that we want. Now remember, we have to imagine that this is written in the format of the integral of 1 over the square root of a squared minus x squared. So in this case, my a squared has to equal 5. So we can take a as being the value root 5. So what I'm then able to do is just use that standard form that we know. So I get that the integral of dx over the square root of 5 minus x squared is equal to sine minus 1 of x over root 5 plus c. Nice, quick, and straightforward. And that depends not on the form that x is written in. As long as we can write it in something that is of this rough format, we're able to do it. If I was to take this here, I'd have to rewrite the bottom such that it was in the format of the square root of a squared minus x squared. Now this x here could be anything. So it could be, an x over a or some function of x, as long as we can write it as something squared. So if I was to take this, what I'd do is I'd want to get rid of the 2 here. So I could take that out as a common factor, and I'd have root 2 times the square root of 5 over 2 minus x squared. So there is my a squared minus x squared there from that one. So from that I'd know that a squared is equal to 5 over 2. So a is equal to the square root of 5 over 2. You could split it off into root 5 over root 2 if you wanted, but I'm just going to keep it in that manner there. So I can then change my integral to 1 over root 2 times the integral of dx over square root of a squared, so 5 over 2 minus x squared. And what I know is that's going to take the same format. I've got 1 over root 2 times sine minus 1. It's x over a, so it's x over square root of 5 over 2 plus c. Rewrite this bit here in the bracket, and I get 1 over root 2 times sine minus 1 of root 2 over 5, keep it as 1 square root, times x plus c. So there you go, written in the same format. For this one I just had to remember dividing by a fraction is the equivalent of timesing by the fraction flipped upside down. Now this one here is the same sort of idea. I want it written such that my square root can be put in the format of a squared minus x squared. And again, this here doesn't matter in terms of its form as long as it can be written as something squared. So if I approach it the exact same way as I did before and have the square roots of 5 minus 2 bracket 3x plus 2 all squared, take 2 out as a common factor, and I get the same as I had before. Root 2 times the square roots of 5 over 2 minus bracket 3x plus 2 squared. Now if I compare these two brackets, they're actually written in the same format. My a squared in this case would still equal 5 over 2. So my a would still be equal to the square roots of 5 over 2. In this case though, my x squared would equal 3x plus 2 squared. So my x, or what would be the equivalent of the x in the formula, would be 3x plus 2. So what I can now do is treat it the same way I did before. Rewrite my integral. I'll have the integral multiplied by 1 over root 2 of dx over the square root of, well now it's going to be 5 over 2 take away the 3x plus 2 all squared. What I know is that that's going to be equal to 1 over root 2 times sine minus 1 of, well it's the x over a, in this case my x is 3x plus 2 and my a is the square root of 5 over 2. And then I'm going to have my plus c. So my answer doesn't take a different format. It's still sine minus 1 of x over a. The only difference is my x and my a are slightly more complex in this example. And when I then simplify all this, I end up getting 1 over root 2 times sine minus 1 of, again, same idea as before, square root of 2 over 5. This time though it's bracket times 3x plus 2, and then plus my constant c at the end of all of that. So I have it written in the format that I want for that one. Again, as I mentioned, it's just a slightly more complex function. So that is if I have it written in that format. Now for the cosine, it would just have to be a negative of that integral. It would follow the same idea. However, tan being written without a square root, that's going to take a slightly different format, which we're going to look at now. So we have to remember that d by dx of tan minus 1x is equal to 1 over x squared plus 1. So if we have it in that format. And again, if we reverse the process and calculate the integral of 1 over x squared plus 1 dx, we get tan minus 1 of x plus c. Now if you think of generalizing it like we did before when it came to calculating the derivative of it, what we're able to do is reverse this process. So if we had tan minus 1 of x over a, and we took the derivative of that, we got a times the integral of 1 over x squared plus a squared. Well, this just reverses that process, and the only part that really changes a bit is what would have been the a in front now becomes a 1 over a to cancel it with the tan minus 1 of x over a to keep it in the right format we want. So let's look at an example. I'll show you what I mean. Let's imagine I want to find the integral of dx over 4 plus x squared. Well, remember what we want is it written in the format of the integral of dx over a squared plus x squared. Now in this case, I know that a squared is equal to 4, a is equal to 2. So what I can do is just use that standard form of the integral and say what that implies is that the integral of dx over 4 plus x squared is equal to 1 over a, so 1 over 2, tan minus 1 of x over a, so x over 2 plus c. So we can just use that standard format in order to be able to get the solution we want quickly, easily and straightforwardly. And it's the same as it would be for the more complex sines ones, where we just have to remember to write it in that generalized format, but the x can be a function in any form we want as long as it's some sort of function squared. So what this leads me on quite nicely is to the fact that I now have set functions that I can calculate the integral of and relate them to the trig functions to a standard format. I know that the integral of 1 over x squared plus a squared dx is going to equal 1 over a tan minus 1 of x over a plus c. The integral of 1 over the square root of a squared minus x squared dx is going to equal sine minus 1 of x over a plus c. And as I mentioned, if there's negative of that, so it's the integral of negative 1 over square root of a squared minus x squared dx, that's going to equal cos minus 1 of x over a plus c. So switch a sign there at the end, it just changes it from a sine to a cos, but the format stays the same. We need to know and memorize and remember these three standard forms, because if we do, it's going to help us a lot when it comes to calculating integrals, because we'll be able to do it in the snap of a finger rather than having to go through a massive process of substitution and working through a lot more material than we need to.